In the past videos, we looked at what fractional factorial designs are, why are they needed, and we also learned something about the aliasing structure that would be needed to construct fractional factorial designs. And we understood what aliasing really meant in terms of getting the effects of the factors, etc. Now, let us dive a bit further into fractional factorial designs. We know that we could construct a half fractional factorial design or a 1/4 fractional factorial design or a 1/8 fractional factorial design, etc. Right? The fraction actually depends on two things. One is the number of factors we have to explore in the system. So that factor is denoted by the symbol k. And we also know the number of experiments that we are able to afford on the system. So if you are able to afford only 2 to the power of k minus p experiments on the system, and you have to explore k factors, and each factor you would like to explore at 2 levels, because that would be the minimum exploration that one can do, what you should do is you need to have this 1 by 2 to the power of p fraction. That is all you can do, and that's what you should do. So if you do a full factorial, you will have to do 2 to the power of k experiments on that system. All right, if you want to test each of them at 2 levels, that's what you got to do. But you have money to do only, or time to do only 2 to the power of k minus p experiments. Therefore, we realize that you have to divide 2 to the power of k by 2 to the power of p in order to match the number of experiments. So this 1 by 2 to the power of p depends on the number of experiments you can do and the number of factors you need to explore in the system. So you could conceive of a design which is like 2 to the power of 6 minus 2, right? Where k is equal to 6 and p is equal to 2. So that would be 1 by 2 to the power of 2 times 2 to the power of 6. All right, so it will be 1/4 of 2 to the power of 6, which is quarter fractional factorial for a full 2 to the power of 6 design. Now, how do we construct, let's say, a 2 to the power of 6 minus 2 design? So first of all, you realize that you're able to do only 2 to the power of 4 experiments. You have 6 factors, k is equal to 6 to explore. These are only the number of experiments you can do, 16 experiments. Therefore, you are forced to consider a 2 to the power of 6 minus 2 experimental design or quarter fractional factorial design. So how do you construct this? First of all, you realize that 2 to the power of 6 minus 2 is 2 to the power of 4. Therefore, start with a full factorial design for the 4 factors, right? For the 4 factors, let the 4 factors we choose be A, B, C, and D. So these are the 4 factors. So you write a standard table corresponding to a full factorial design on those 4 factors. All right. Then you add columns E and column F, because you have to set the levels or settings for the factors E and F also, because you have to explore 6 factors. So then what you do is you have to use design generators for the settings of factors E and F. So that is the choice that we have, and we have to use that choice wisely so that you get a good high resolution design. That means you want good aliases to exist in your problem. So if you choose the generators for E and F unwisely, then we will get designs that are poor in resolution, or in simple words, we will get a bad alias structure. Okay, so for E and F, for each of them, you have to have a design generator. So that is our choice. So in this particular case, what happens is the design generators have been so chosen, right? I or 1 equals A, B, C, E. In other words, if you multiply both the sides by E, you will get E is equal to A, B, C, E times E. So we can call it E squared, and we recognize E squared is going to be equal to 1. when you're doing 2 to the power of 2 design, for example, you will have e at -1 and +1, right? So whenever you're testing at two levels in terms of coded variables, we would have any factor to be either -1 or +1. Whatever be it, -1 or +1, square of that is going to be +1. Therefore, e squared is going to be equal to 1. Therefore, e is equal to ABC. That's the design of the e column. So what you do is, to get this entry for e for the first experiment, you take the first element of A, it could be minus or plus. You take the first element of B, which could be minus or plus. You take the first element of C, which could be minus or plus, and then you multiply those three numbers to get this entry for E. For the 16th, if you want to get this, entry for E, you could take the 16th entry of A, the 16th entry of B, and the 16th entry of C, and you multiply those three numbers. Each of the numbers could be -1 or +1, and you can get the entry for the 16th element of E. So that is how you get the settings for factor E. For factor F, they have used this design generator. This was the choice. Therefore, you could say in the similar way that we did for E, we could show that F is equal to BCD. So you take elements of BCD, corresponding entries in BCD, and you can fill up the F column by multiplying those three entries, corresponding entries in BCD columns. You could get the entries filled out for column F. So these are the design generators. I is equal to ABCE and I is equal to BCDF. And by this choice, we will also get another defining relation, right? Another defining relation which you could take. For example, I is equal to ABCE is our first generator, and I is equal to BCDF is our second generator. So we need two generators because we are doing 1 by 2 to the power of 2 times 2 to the power of 6 design. Since we are doing 1 by 2 to the power of 2 times 2 to the power of k design, we would need two generators, right, to kind of get going. Therefore, these are the two generators that are used. If you take these two and you multiply them, the left hand side, I into I gives you I. The right hand sides, if you multiply, you will get A, B squared, C squared, D, E, F. Correct? And we recognize that B squared and C squared are both equal to 1. Therefore, you will get another design generator or a defining relation, which is I is equal to A, D, E, F, which is what is shown here. Okay, so you have the basic design generators that would depend on the p-value. Okay, and on top of that, you can take those basic generators, right, these two, and you multiply them to get the new defining relationships for the system. So we have these three defining relationships for the system. I is equal to ABC equals BCDF equals ADEF. Now, each of these terms is called a word. So this is called a word, this is called a word, this is called a word. So the resolution, this is a formal definition of the resolution of a 2 to the power of k minus p design. It is equal to the number of letters in the shortest word. Okay. So here, if you take the three words, ABCE has a length of 4, BCDF has a length of 4, ADEF has a length of 4. So the minimum of these three is 4, right? So this design that we have constructed with these basic generators, that would be a resolution 4 design. It is indicated with a Roman numeral. So we would say 2 to the power of 6 minus 2. The design in Roman numerals 4. So this people will understand is the resolution of this design. So it tells us something about the aliasing structure or the nature of our design. So we know that, right, 2 to the power of 6, the 6 will denote the number of factors. This 2 will denote the fraction that we are aiming for. So this is equal to P, this is equal to K, and this is equal to the resolution. Okay, So the resolution is quite important because you can have the same 2 to the power of 6 minus 2 design, but with lower resolutions. That means with poorer aliasing structures. So whenever we construct the fractional factorial designs, you should strive to maximize the resolution as far as possible, right? So that is the idea. So here I'm just taking the material from the previous slide. So what we have defined there is a resolution 4 design. So let's write out its complete alias structure. So I is equal to ABCE equals BCDF is equal to ADEF. These are the design relations, right? These first and second were the ones we used to generate the column E and F. And from those two generators, we got this generator as well, okay? ADEF. Now we can get the alias structure by using this. For example, if I take I is equal to ABCE and I multiply it with A, I will get A is equal to A squared BCE, which will be BCE. And if I take I is equal to ADEF and I multiply it with A, I will get A is equal to DEF, right? You understand? So I take I is equal to ADEF and then I multiply both sides by A, I will get A is equal to DEF. Okay. I can also take I is equal to BCDF and multiply both sides by A to get A is equal to ABCDF. So that is what is shown here. You could do the same thing for the other things. I've just shown you here that A equals BCE equals DEF is equal to ABCDF. How did I get this? By taking the design relationships for the system, right? We have three of them, two defined by the basic design generators and one is a derived generator, right? So using that, multiplying both sides by A, I get all these relationships. So kindly make sure you get all these alias structures that you see listed in that particular table. Okay, so take a moment to generate, let's say, for example, this. Make sure this makes sense to you. All right, so now what do we see? We see here that the first order terms, right, or the direct effects are aliased with either 3-factor interactions or 5-factor interactions. That's not bad. Okay, so we don't see a direct effect alias with another direct effect or even with 2-factor interactions. All right, so A, B, C, D, E, F, the direct effects are aliased with 3rd-order interactions or 5th-order interactions. 3rd-order interactions are aliased with other 3rd-order interactions, as you can see here. 2nd-order interactions are kind of aliased with other 2nd-order interactions or 4th-order interactions or 6th-order interactions, etc. So we are very happy that this design has this alias structure where no direct effect is aliased with another direct effect or even 2nd-order effects. Okay, so that is what this good design is about. And you can design other 2 to the power of 6 minus 2 designs using other design generators, and you can find its resolution using the method that was suggested earlier. And you could also write down the complete alias structure, and you will see it is similar or worse than what we have in this particular table here. Okay, so generate other designs, 2 to the power of 6 minus 2 designs, and convince yourself you are probably not going to do better in the alias structure than what we see here. We simply do not want the direct effects to be aliased with other direct effects or the direct effects aliased with 2nd-order interactions, because direct and 2nd-order interactions are the most important effects in many systems. All right. So, and we also understand that aliasing is unavoidable. If you can do only 2 to the power of k minus p experiments, but you have k factors, aliasing is unavoidable. So then we aim for good aliasing, and that is what this whole thing is about. So if you take a look at this, each of this rows has 4 elements, as you can see. All right, has 4 elements. So you see this 15 of them, I suppose, right? 4 here, 4 here, 4 here, and 3 here. So this is 15 times 4, you have 60. And then you have I, right? A, B, C, E, B, C, D, F, and A, D, E, F. So you have a total of 64 elements here. So what does this say? The constant term in the model is going to be aliased with the 4-factor effects that we see here, 4-factor interaction effects. So that is what this means, right? I is equal to A, B, C, E is equal to B, C, D, F is equal to A, D, E, F. This I stands for the constant term in the model. So that constant term, which can also be important, is aliased with higher order interactions, 4th order interactions to be specific. And 4th order interactions, we assume, or we have seen in many systems, that 4th order interaction effects are very small. Therefore, this aliasing is okay. So in 2 to the power of 6, you will have 64 experiments. So you can estimate 64 effects, constant, direct effects, 2nd order interaction effects, all the way till 6th order interaction effects. So you'll have 64 of them, and you see the 64 of those interactions here, all of those interactions here, and the aliases that are existing between these 64 effects. Idea of design resolution, right, is to catalog fractional factorial designs according to the alias patterns they produce. So higher resolution means better alias pattern. And typically, right, in practical applications in chemical engineering, design resolutions 3, 4, and 5 are particularly important. The idea is typically we work with certain number of factors, right? And typically, what you see here is this 2 to the power of k minus p. This k minus p is typically of the order of 3, 4, or 5. Okay, so that is the idea. Therefore, these are particularly important in many chemical engineering applications because k minus p is typically of the order of 3, 4, or 5. All right. So we have seen this already. The resolution is equal to the number of letters in the shortest word in the complete defining relation. So a 2 to the power of 3 minus 1 design with I is equal to ABC. Does this make sense to us? So we are going for a 2 to the power of 3 minus 1 design. In this case, k is equal to 3 and p is equal to 1. That means we have 3 factors. Ideally, we would have liked to do 8 experiments, 2 to the power of 3 experiments, each factor tested at 2 levels. And we would have liked to find out the direct effects, the 2-factor interaction effects, the 3-factor interaction effects, etc. But let's say we have resources to do only 4 experiments. Therefore, we have to resort to 2 to the power of 3 minus 1 design. And to get a 2 to the power of 3 minus 1 design, since p is equal to 1, we will have one design generator. Let's say the person chooses I is equal to ABC to be the design generator. In other words, the person chooses the C column to be A times B. That's what it means. So what I will do is I'll start with A and B. I will do a full factorial design on 2 factors. So minus 1 plus 1 minus 1 plus 1. And then B would be minus 1 minus 1 plus 1 plus 1. So this is a standard 2 to the power of 2 design. So I'll generate C according to this formula. C is equal to A times B. So C will be equal to 1 minus 1 minus 1 and 1, right? By multiplying the corresponding entries, you would get this. So the first experiment in this table is A and B set at their low levels and C set at the highest level. And experiment 3, you have to do it all in random order. I'm just mentioning it in the order of the standard table. The third listed experiment will have low settings for A factor and C factor and high settings for the B factor. All right. Since I is equal to ABC is the only design generator, and this happens to be a 3-letter word, and therefore the resolution of this design is 3, and therefore we would write 2 to the power of 3 minus 1 and include the resolution at the bottom. So whenever you denote a fractional factorial design, you should also indicate the resolution using Roman numerals at the bottom as a subscript there. So a 2 to the power of 4 minus 1 design with I is equal to A, B, C, D as the generator will be a 2 to the power of 4 minus 1 subscript 4. A 2 to the power of 5 minus 1 design with this design generator where E is equal to A, B, C, D, that would be a resolution 5 design. All right, because we have chosen like this. In this case, I could have chosen, and nobody can stop me. I can say E is going to be not A, B, C, D, which is what is suggested here. I'm going to say E is equal to A, B, C. Is there anything wrong with it? No. In a sense, I have the right to choose I is equal to A, B, C, E, and therefore E is equal to A, B, C as the way to generate the E column. But then you already see that this is going to be worse, right, compared to this, right? You can write the alias structure and you can see that this will lead to a poor resolution. A previous example that we saw for a 2 to the power of 6 minus 2 design with these to be the design generators has a resolution 4 design. 4 word, 4 word, 4 words, and therefore the minimum of these 3 is 4, which is the resolution of the design. So when we go for P more than 1, P is equal to 2 or 3 or 4, things become very interesting. For P is equal to 1, it's not as interesting. Okay. Now, if for the 2 to the power of 6 minus 2 design, I use these as the basic design generators. That means E is equal to A, B, C is how I define the E column, and F is equal to A, B, C, D is how I generate the F column. So in other words, I use these as the basic or initial design generators, right? So I use these two. What would be the generalized interaction? The generalized interaction would be if you take I is equal to A, B, C, E and I is equal to A, B, C, D, F. Now if I multiply the two, right, I will get I is equal to A squared, B squared, C squared, D, E, F, which will reduce to I is equal to D, E, F. That's what I write here. And if you look at this entire thing, this is 4-letter word. This has 5 words and this has 3 words. So the minimum of these 3 numbers is 3. Therefore, if I use this as the basic design generators, I will get a resolution 3 design. So it's still 2 to the power of 6 minus 2, but it has got a lower resolution than the example we saw earlier. So the alias structure for this new design will be poorer than the alias structure we had for the previous choice of design generators. So a resolution 4 design is better than a resolution 3 design simply because this has a better or safer alias structure. Both the designs are 6 minus 2 designs. So the number of experiments is the same, the number of factors is the same. But how we choose to generate the E and F columns here makes a difference in the alias structure and therefore in the resolution of the experimental design. So this is an example. It has got 6 input factors A, B, C, D, E, F, right? And the response variable is not shown here, but there is a response variable. But the factors are these 6 factors, and a total of 32 experiments are shown here, right? So 32 experiments are performed. So what is the resolution of this experimental design is something we can see. So for example, number of experiments is 2 to the power of 5 because 2 to the power of 5 is 32. If you do full experimental design, you would have 2 to the power of 6 experiments, which is 64. So what has happened here is K is equal to 6, P is equal to 1 because 2 to the power of 5 is 2 to the power of 6 by 2 to the power of 1. So this is going to be 2 to the power of 6 minus 1. So look at this design and see how the F column was generated. Okay, so just make sure that columns A, B, C, D, and E correspond to the standard 2 to the power of 5 full design. And then see, for example, how this factor F was generated. And then that will tell you what is the design generator and therefore what is the resolution of that design. Now, if you go for general 2 to the power of k minus p designs, what you see here is the following. So far we have looked at something like 2 to the power of 6 minus 2 in some detail. We have looked at 2 to the power of 5 minus 1, 2 to the power of 4 minus 1, 2 to the power of 3 minus 1, etc. But now let's go into the general 2 to the power of k minus p design. So the statement we make is you will have to have p independent generators, right? Because for p columns, you must write generators, right? You must write generators. So you will have for k minus p columns, you can do a standard design, and then you have to fill out p columns using design generators. So you will have p independent generators. And if you take p independent generators and you process them, you will get these many generalized interactions. So we can prove this, right? So in particular, let's say we took I is equal to, let me take this example that is shown in this particular slide. So there's a 7-factor experiment, and they are doing quarter of 2 to the power of 7 design. So k is equal to 7 here, p is equal to 2 here, and they show 3 designs. The question is, which one is better? We'll come to that later, but let's take just the design generator for design A, right, as an example. So you have to do 7 to the power of 2 design. So k is equal to 7 and p is equal to 2. So I can write a standard 2 to the power of 5 design. And for the other 2 columns, right, columns F and G, right? Because A, B, C, D, E will be filled out by a standard 2 to the power of 5 design matrix. For columns F and G, the last 2 columns, because P is equal to 2, I have to use design generators. So what these people have used is I is equal to A, B, C, F is one design, and I is equal to B, C, D, G is another design. So that is what they've used, because you need 2 design generators. In other words, they are saying F is equal to A, B, C. I'm going to generate column F using the entries in A, B, C columns, and I'm going to generate the settings for the G column using B, C, D, right? So that is what it means. So these are the 2 basic generators. All right. Now I can multiply the 2 to get I is equal to A, D, F, G, right? Because B squared and C squared will equal 1. So I just multiply these 2 to get I is equal to A, D, F, G, which is what is indicated here. So we know it's a resolution 4 design, because if you look at the design generators, all of them have word length of 4. Okay, fine. Now, how many generalized interactions we have? So we have these 2 independent generators. Okay, so that is okay. Now we have one more here, right, which we get by multiplying these 2. That's how we get this third one. So how much is this? 2 to the power of 2, because P is 2 here, minus 2 minus 1. So 2 to the power of 2 is 4, minus 2 is 2, minus 1 is 1. So we have one generalized interaction that we get from these 2. So in general, if you have P independent generators, for example, if P is equal to 3, that means we are doing 1/8 fractional factorial. If P is equal to 3, in addition to the 3 independent generators that we have to choose, you can also process those independent generators to get these many generalized interactions. So when P is equal to 3, you will have 2 to the power of 3 minus 3 minus 1, which is going to be 4 generalized interactions. Let's try to do an example to see that. Let us say we are aiming for a 2 to the power of 8 minus 3 design. So k is equal to 8 and p is equal to 3. Now we have A, B, C, D, E generated as a full factorial design. So we can get this, right? So we can write out the 32 experiments that correspond to the full factorial design in the 5 factors. Now we use design generators for F, G, and H. Right? So for these three, we have to come up with design generators. So let's say for F, I choose, just as an example, I choose F is equal to ABC, for example, right? I'm not trying to be designing a high resolution design. So I'm just choosing this as normal choices. So G will be equal to, let's say, BCD, and I choose H is equal to CDE, right? So let's say I come up with this with these choices. Now, if you take these three basic or independent generators, I'm going to have I is equal to A, B, C, F. I is equal to B, C, D, G, and I is equal to C, D, E, H. So these are the other ways of writing the design generators. Now I can take, let's say, I'll call this as D1, basic generator 1. So let's call this BD1, this is BD2, and this is BD3, basic design generators, right? Basic designs, BD1, BD2, and BD3. Now I can multiply BD1 with BD2 to get a new generator. I can multiply BD1 with BD3, and I can multiply BD2 with BD3 to get the three generalized interactions. And then I can take BD1 multiplied with BD2 and multiply it with BD3 to get another generalized interaction. All right. So if I do the last one, it will be like taking the three basic generators, multiplying the left hand side. So I is equal to I multiplied by I, which will be equal to I, is equal to ABCF multiplying with BCDG, and that multiplies with CDEH, because these are the three basic generators. So now BC here will multiply it with BC here to get B squared C squared, and that will go away. And then you can take this D and this D, right? And they will go away. So you might be left with A, F, G, C, E, H. So that will be a one of the words, right? So I is equal to, in this case, if I've done it right, it will be A times F times G times C, E, H. So if you put it in a proper order, so it will be A, C, E, F, G, H. That will be the new word that we create. So that's a generalized interaction. So here 2 to the power of 3 is 8, minus 3 minus 1, you have these 4 generalized interactions that you can get out of the P basic design generators. All right, so this is how this statement comes into play. All right, we can formally, if you want, you can do it and show that you will have 2 to the power of P minus 1 generalized interactions. So totally you will have 2 to the power of P, right, minus 1 interactions overall. Why? Because this P and this minus P, you add, they kind of cancel each other. So you're left with a total of 2 to the power of minus 2 to the power of P minus 1 overall number of interactions, all right, or generators. But out of them, the P ones are the ones you choose originally. Those are the independent generators. Now, out of these three designs, which design is good? All of them are resolution 4 design, because if you take this, the minimum is 4. If you take design B, the minimum word length is 4. If you take this design C, the minimum word length is 4. the longest link doesn't matter. Okay, so we are looking at the weakest link. So therefore, we are looking at the shortest word. And in all these three designs, design A, B, C, which are having two basic generators, all have a resolution of 4. Now the question is, which of these is good? All right, so that is the question we need to answer. All right, are all of these the same or these different? Okay, so I would like you to ponder about this, and we can discuss about it at a face-to-face session. So let's look at 2 to the power of 7 minus 4 design, and this is of resolution 3, and they have these generators. So if you have 2 to the power of 7 minus 4 design, that means you have 7 factors, your p-value is 4. That means you are at liberty to design ABC. So that's the basic design, right? So you have 2 to the power of 3 design, full factorial on those 3 factors. So you see this is a very familiar table for us, or a familiar matrix for us. A goes minus plus minus plus minus plus minus plus, B goes minus minus plus plus minus minus plus plus, and C goes minus 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 plus 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 plus. So this is familiar to us. And then using the generators that we choose, we can generate columns, settings for columns D, E, F, and G. And that is what this table shows. So the basic generators here should be 4 of them. So I is equal to ABD was a choice, I is equal to ACE was a choice, I is equal to BCF, and I is equal to ABCG were the choices. So in other words, D is nothing but equal to AB, E is nothing but equal to AC, F is nothing but equal to BC, and G is nothing but ABC. So this is how these 4 columns have been filled out, right? This column, this column, this column, and this column have been filled out. So, and you understand why this is written as DEF, because in the run 1, D, E, and F are at the high values. The other factors are at their lower settings, to be precise. And therefore, you have these kind of representations for labels of those experiments. So you write the basic generators, which are 4 of them. And since P is equal to 4, you must have 2 to the power of P minus 1, which is equal to 2 to the power of 4, because P is equal to 4 here. You will have 16 minus 4 minus 1. So you should have 11 generalized interactions beyond these 4. Okay, so now if you take ABD and multiply it with ACE, you will get A squared BCDE. So you will get BCDE. So that is what you get here. If you take ABD and you multiply it with BCF, you would get ACDF, which is what you see here. And if you take ABD and multiply it with ABCG, you will get CDG, which is what is shown here. And so on. So once we are done with this, this, and this, then you take ACE and multiply it with BCF. So you will get ABEF, which is what is shown here. All right. And then you take ACE and multiply it with ABCG. So you're doing this. So you're going to get A squared BC squared EG, which is going to be BEG, which is what you see here. So likewise, you proceed. And then you take BCF and multiply it with ABCG, you will get AFG, which is what is shown here. And then you're done with taking the two of these and multiplying it with each other. Now what you can do is you can take 3 of them, right? You take 3 of them and you multiply, and then you will get a relationship. So after this 3, you can take this, and this, that makes another 3. You can take this, this, and this. You can make another 3, etc. Right? So you can look at the 3 things, and then you take all the 4 basic generators and you multiply to get another derived generator. So if you do that, you will see you will have all the 11 derived design generators, making a total of 15, right? Making a total of 15 because 2 to the power of p minus 1 will be 15 overall. So you have p independent generators, then you have 2 to the power of p minus 1 derived generators, and if you add these two, you will get 2 to the power of p minus 1. And when p is equal to 4, like in this example, you will have 15 of them. So if you want to get the alias effect, so once you have generated these, what do you call the total number of design generators, all right? So what you do is you can take this, because this contains all of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, all the 15 of them, with the green ones, the ones underlined in green being the basic generators. So these are the 4 basic generators, and the ones underlined in red are the derived generators, making a total of 15. So you take this particular thing, and that's what I show on the next slide. And then if you want to find the alias for B, all you do is you take this relationship, right? You take this relationship and you multiply all the terms with B. So I multiplied by B will give you B. ABD multiplied with B will give you AD. ACE multiplied with B will give you ABCE, etc. So you can write the entire alias structure for B. You can do it for C, you can do it for A, you can do it for AB, you know, whatever. And you will get the overall alias structure for the design that you have. And this one is particularly dangerous somewhat, right? This particular design generator is dangerous. We have to see whether we can get a better one. But this one is dangerous because a direct effect is aliased with other second order interaction effects, and second order interaction effects could be important in systems. Therefore, you would not be able to tease out the effect of B from the effect of AD, CF, or EG in this particular design of the experiment. Okay, but sometimes you will have no choice because you are not doing as many experiments as you would like to do, and therefore you have to live with the alias structure that is there. But to the extent possible, use design generators that will give you better aliases and better resolution. That is the key. Okay, so what we are doing here is we are taking the same system, a system with 6 factors, and we are doing 32 experiments. So we are doing half of what is the full factorial design. So we are doing half fraction design. And the task here for us is to elucidate the alias structure of this design and to find the resolution, etc. Right? So that is a continuation of the previous problem. I will leave you with this exercise that comes from a semiconductor manufacturing scenario where there are 6 variables, right, that needs to be explored. So K is equal to 6, and the high and low levels for each of the factors and the description of the factors are all indicated there. And the entire data set is given here. Okay, so you have these input factors in this column. So you do only 32 experiments. So this is an expanded version of the data that was given to you earlier. So we have included these outcomes or the response of the system in terms of resist thickness. So we have the resist thickness measured at 3 locations on any chip, for example, and then the average value is also provided for us, and the range is also provided for us. So range is nothing, as you know, the highest value minus the lowest value, right? So that's the range. So that's also indicated for us here. So, and then we need to answer these questions. So verify this is a 2 to the power of 6 minus 1 design and discuss the alias relationships in this design. Then you need to find out the important factors that affect the average resist thickness. So they are asking questions using average resist thickness as the response variable, and a bunch of questions following that. Okay, And finally, you are supposed to provide a recommendation for how you would like the process engineers to kind of operate this process so as to get the outcomes of their choice, right? So the question is, do they want the average resist to be high or average resist to be low? And to get there, what should be done, right? How should these 6 factors or the important factors in the setup be positioned so that we could get the um, outcomes that we want in the plant? So I will stop here and we'll pick up the discussion at a future session. Thank you.